Okay. Hello, everyone. Let us see how we will talk or how things will go with quantum linear regression. All of us are aware of linear regression and the properties involved with the regression coefficients, etc. What exactly is linear regression is, suppose if I am considering a problem, then we try to predict the continuous value of the variable yi. We try to predict the continuous value yi of the variable yi for a given set of input features x, x1, x2, and so on, xn. For given input xi, I am writing it in superfix, I ranging from 1 to capital N. Okay. Yeah. Where capital N, I mean this x, which has all the n values, would be an input vector, and x belongs to the Rn space. Okay, there we are talking about things in real line. Okay, yeah. Now in linear regression, we consider the output to be a linear combination of the input features. That is represented by this equation. Okay, I'll just call this to be 1. Linear combination of the input features with some irreducible error component. Of course, I'm writing it in terms of n terms only. Then there can be n plus 1, n plus 2, and so on. Hence, there will be error also. Actually, if I write it like this, y is equal to mx plus c kind. Okay, linear. Of course, an error is involved because I am talking only about n values. There can be n plus 1 and above. Okay. Hence, arises my error. Okay, now this is the equation given by 1. Of course, in shorthand notation, I can write it like summation I is equal to 1 to capital N theta I x power I plus B plus EI. Okay, the theta I corresponding to each feature and the intercept B are the parameters to the model that we want to learn. Okay, this M and C is what I will interpret. Of course, here I am denoting it by theta. So the theta I feature and the intercept B are the parameters to the model that we want to learn, or we interpret, or we try to find. Okay, suppose if the parameter theta I for I is equal to 1, 2, and so on till capital N. Of course, it's a vector, be a vector. And this theta belongs to again Rn space. Then what we can do is we can further simplify the linear relationship as yi. Of course, I divide throughout by xi. This is equal to theta transpose xi plus b plus ei. Okay. Suppose if I am representing this theta I by a vector theta which belongs to Rn space, instead of theta I say it is just theta. Then what I can do is I can rewrite the above relationship. What exactly I am trying to do is I am trying to multiply with theta transpose. Okay, I'm rewriting the summation theta I is equal to 1 to n by theta transpose. Okay, what happens now? There are certain things that I need to consider. What that is yi by xi. This value stands for yi conditioned on xi. Yi conditioned on xi. Of course, ei is I cannot reduce ei because it is error. I can say here irreducible component. I cannot minimize this. It is compulsory. And of course, it doesn't have any relationship with the parameters that I have considered or the input features that I have considered. Okay. Now, given xi what we need to determine is the term theta transpose xi plus b. Of course, what I will do here, what depends on the methods. Here we are assuming that the error ei follows normal distribution. Normal distribution. As all of us know, normal distribution has zero mean and some finite standard deviation sigma. Okay, that is what, how do I denote it? Ei follows normal distribution. So 0 and sigma squared. Of course, sometimes we take this to be 1 and so on, depending on the case. Okay, now theta transpose xi plus b is a constant. Given the value of the feature xi. Suppose if I know the value of the feature xi, then it turns out to be a constant value, right? Is a constant given the value of xi. Okay. So theta transpose xi plus b plus ei, I can say like this. Theta transpose xi plus b comma sigma square. Okay. Now, what is the value on the LHS? The value on the LHS is nothing but yi by xi. This follows normal distribution. Xi plus b comma sigma square. Okay. The target label yi given by the input feature follows normal distribution with mean theta transpose xi plus b and standard deviation sigma or variance sigma square. In linear regression, we take the conditional mean of the distribution as our prediction. Okay, we will take the conditional mean in linear regression. Now here what I can say, yi follows normal distribution with the mean theta transpose xi plus b and standard deviation sigma. Variance is sigma square, standard deviation is sigma. Okay. For linear regression, what do I do? For linear regression, we take the conditional mean. We take the conditional mean of the distribution as our prediction. Of the distribution as our prediction. Okay, what that is yi cap, this is equal to expectation. Mean is given by expectation. Another name for it is theta transpose xi plus b. The parameters of the model theta and bi can be determined by minimizing the sum of squares of the error. Of course, linear regression or curve fitting have direct and indirect relationships with sum of least squares where we try to minimize the error. So what exactly here I am trying to say is the parameters of the model, of this model, theta and b can be determined by minimizing the sum of squares of the error term. I try to minimize the error term for each data point. Okay. For the ease of the notation, we can consume the bias term b as the parameter within the theta parameter vector corresponding to the constant feature of 1. Okay. Or what exactly I'm talking about, let me write here. The parameters, of course, as mentioned earlier, the parameters to be determined are theta and b or bi, whatever. Theta and b. The parameters can be determined by minimizing the square of the error term. Square of the error term EI. Square of the error term EI for each data point. For each data point. Of course, we are aware that usually one value at one point, one function value at one point, usually for classical computing, right? But for quantum can take multiple values at a time and give multiple function values at a time. Okay, that's the benefit of quantum. Yeah. So what we do is, as I was mentioning, for ease of notation, we consume the bias term B as the parameter within the theta parameter vector corresponding to the constant feature of 1. Hence, with this prediction, what happens would be yi cap is equal to theta transpose xi. Okay, where theta and xi are n plus 1 dimensional vectors, where theta and xi both are n plus 1 dimensional vectors. Okay. Now, the matrix notation for this. So that it looks like system of equations, etc. How do I write the matrix notation? Just see here. X1 transpose, X2 transpose, and so on. Xm transpose theta. This is equal to y1 cap, y2 cap, and so on. Y capital M cap. Okay. The matrix representation looks something like this. Now, if we represent the matrix with the input features in the equation that I have written above, I mean, if we represent the matrix with the input features in this format, I call this to be 2. Then capital X belongs to R power capital M cross n plus 1, because I said theta and xi are n plus 1 dimensional vectors, and the prediction vector yi cap would belong to R power M. Okay, because theta transpose xi would make a matrix, right? So hence I rewrite this as x theta is equal to capital Y cap. Okay. Yeah. Now, if I want to know the error also, I know clearly what's the difference. Error would be the original Y minus the interpreted Y. Okay, not the small y. Observed minus expected kind. Okay. And then what is it? Y minus x theta. Okay. Now, the loss objective can be written as the mean of the squared errors in the prediction for the each data point. At the end, I will just give a just what exactly we are trying to do. The loss objective, I call it to be L theta. It is nothing but the square of errors at each data point. Okay, so EI squared, sum of all the squares of errors. Okay, the previous loss is nothing but the average of the dot product of the error vector with itself. What I mean to say is E belongs to something like Rm. It's a vector, right? It's a dot product. If I take, how will the dot product look like? Something like this? Yes. So I know what is E. 1 by M capital Y minus x theta transpose into capital Y minus x theta. Okay. So to determine the parameter theta, we need to minimize the loss L theta with respect to theta. To determine the minima, we take the gradient of the loss with respect to the theta and set it to 0 vector as shown. Okay, I will just show gradient of the loss vector. Okay, gradient of the loss. In shorthand notation, I will write like this. This is nothing but minus 2 by m x transpose y minus x theta. This I am equating it to 0. Hence, what I will be getting is something like this. X transpose x into theta. This is equal to x transpose y. What I will be getting is x transpose x is equal to. What exactly I have done is just to differentiate it. I mean, considered the Laplacian or the gradient, right? Partially we are aware of gradient, right? What del stands for, we know. I'll just put summation instead of writing the whole thing. Now, x transpose x. If at all, if my x is Hermitian in nature, then we can say that the quantum system is Hamiltonian. Okay. And then we can solve the matrix inversion problem to find the model parameter theta. Of course, as mentioned in my previous video, the HHL, using the HHL algorithm, we will try to find the model parameter theta using HHL algorithm. Let me write the points that I have told here. If x transpose x is Hermitian, what is the Hermitian matrix? Conjugate transpose. Suppose if A is a matrix, let me write like this. Its conjugate transpose, of course, would be denoted by theta, should be equal to A. Okay, it's exactly like your symmetric matrix in real, right? If x transpose x is Hermitian in nature, that means what? I'm talking about, till now I have considered things in real line. Now I'm talking about Hermitian, where things are transforming into complex plane, and hence, once I talk about things in complex, then quantum also comes into picture. That's why if x transpose x is Hermitian, then it can be treated as, then I can treat this, then it can be treated as Hamiltonian for a quantum system. For a quantum system. Once I say it's a quantum system, then a matrix inversion problem can be solved using HHL algorithm. What exactly is HHL? Of course, I'll not elaborate that the names of HHL. Of course, they are named after those people who have invented it. What exactly is HHL algorithm? As it is used to solve linear system of equations. Now, what exactly I want here is, I want to solve for theta, right? So to find theta, what I will do when I'm talking, as mentioned, to solve for theta, we use HHL algorithm. We use HHL algorithm. Okay, I hope you have understood. Otherwise, I can just put in a gist. Of course, first I have started with linear regression only. Then at the end, after doing certain things, I made the concept slowly correlatable to complex plane. And then when things come to complex, or when I talk about Hermitian things, then it means that when I'm in complex, then I can talk about a quantum system. Once I'm in a quantum system, then things related to quantum system can be applied. And then HHL algorithm is famous for solving system of equations in quantum. Okay. Hence, I go for getting theta, of course, matrix inversion or whatever. The matrix inversion problem. problem to find theta. Find theta can be done using HHL algorithm. Okay. What exactly in gist is, first, normally a data is being given. No one is aware. No one gives a data in terms of kets or states. The notation that we use in quantum, guys. Hence, what I will do, first normal data is being given. Then I encode the data as a quantum state. Now, once I encode the data as a quantum state, after encoding the data, I form the linear system. Once a linear system is formed, I have a method in quantum to solve a linear system. That is my HHL algorithm. Once I apply HHL algorithm, I get the answer. I get the values, I measure them, and hence predict the solution for the given system. That's what is exactly quantum linear regression. Normally, in normal linear regression, I have just values or numbers, but here I'll be having kets or states. I'll not be having, I'll be encoding the given data in terms of states or kets that a quantum system understands, and then proceed with the different things. Of course, I can write in just what exactly I was talking about as a flow chart. Encode data. Step 1 is encode the given data, encode the given data as quantum states. Quantum states. That's the first step. The next step is form the linear system. Form the linear system. Okay, next is apply HHL algorithm. Apply HHL algorithm. Of course, this algorithm is neither unsupervised nor supervised, guys. Quantum linear regression, of course, you can just guess whether it is supervised or unsupervised, guys. Again, when I talk about quantum linear regression, then I should tell whether it is supervised or unsupervised. You can just have a guess. Okay. Apply HHL algorithm. And once I get the output, measure and predict. Measure and predict. This is the outline for the quantum linear regression. Okay. Yeah. With this, I will just stop this video. We'll do some more things in the next one. Thank you.